hate to admit it, but there are some things in the museum that some may find less appealing than others. Of course, the engines are always a huge draw, and they're always a crowd pleaser. But can a ball bearing capture the same attention? Of course not. A ball bearing is just a metal ball, but its story and what it's connected to, I hope, may be enough to change a few opinions. The Isle of Anglesey sits at the tip of North Wales and has seen human habitation for thousands of years. It's separated by the Menai Strait, a rather dangerous stretch of water. The two entrances of the strait have natural differing tides, which in turn can cause very strong currents. As the currents are fighting each other, whirlpools regularly form. The many wrecks that have fallen foul of these currents also don't help. By the start of the Industrial Revolution, it was decided that ferrying people to and fro across the strait was simply not economical, and the tides were making it especially dangerous. In addition, one of the largest sources of income for the island was through the sale of cattle. To move the cattle across the strait, they were driven down to the water and forced to swim. In the currents, the animals were lucky to reach the other side. The 1800 Acta Union was also a problem for the island. Its largest port, Holyhead, was one of the principal ports serving Ireland, and following this union, the government passed an act meaning that a road must be built with a continuous link to London. This meant only one thing: bridging the strait. It was down to Scottish engineer Thomas Telford to solve the problem. He was already an accomplished canal builder, but he had turned his attention to road building and was known as the Colossus of Roads. He calculated both the shortest and tallest route so that the sailing ships could pass under freely, and proposed the largest suspension bridge of its time to be constructed. Work was completed in 1826. It was heralded to be one of the jewels in Telford's crown. The bridge did exactly as planned, but as railways grew in popularity, it was clear that rail links to the island was also a necessity. The road bridge couldn't take rail, so an additional bridge was going to be needed. Telford's bridge was occupying the shortest spot, so the next best thing was required. It also had to meet the height requirements set by the Admiralty. Robert Stephenson was hand-picked for the task and drew up a plan to the problem. He conversed his plan with fellow engineer Isambard Kingdom Brunel, who remarked, "If your bridge is a success, then mine are magnificent failures." You see, Stephenson's plan was, rather than have the trains traverse on the deck of the bridge, as per the norm, was instead to travel through it. But why? Well, it was simple. The Admiralty permitted the bridge under one caveat: that the strait must always remain open to any passing ship, including the tallest ones. This meant the standard viaduct plans were out the window, as a central piers in the water would not only close and disrupt strait to traffic, but it was not known how these underwater pillars would affect the turbulent waters. Stephenson conceded that he must have a central pillar, and there was only one location that would meet every requirement. The land was desirable and could meet the height requirements. It was a large span, but not the largest offered, and more importantly, centred in the middle was a small rocky island, perfect for a central pillar to be built. Stephenson consulted William Fairbairn, Heaton Hodgkinson and Edwin Clark to help with the bridge. Hodgkinson and Fairbairn recommended the use of corrugated metal for the tubes. Corrugated metal was structurally more sound than other designs. Stephenson wanted the tubes to be able to take their own weight, then 2,000 tons more spread across its length. Even the heaviest locomotive in the world would be no problem for this bridge. Initially, the experts, concerned about the strength of the bridge, wanted to support the tubes with metal suspension chains. He assured the board that the piers would do their job and hold the tubes, but the board was sceptical. So Stephenson built a mock-up model and convinced everyone that the chains were needed. Work began on the 10th of April 1846, and the work was overseen by Edwin Clark. Edwin helped Stephenson with the more complex tasks of the mechanical calculations that were needed for the bridge to work. All he had to do was move what he had from paper to reality. Each tube was constructed nearby on the shoreline, and when the section was complete, it was floated into the Strait and under the bridge, where it was hoisted into position. The jacks would only lift the pieces a few inches at a time, so the section was packed underneath. It took nearly a year for the tubes to get in the right position, but once it were done, the pieces sat on metal girders protruding from the bridge and were riveted together to form a continuous tube. The roof and the base of the tubes were made hollow and supported by girders. On the 5th of March 1846, Stevenson himself pushed the very last rivet into place, marking the completion of the bridge. At first, only one tube were opened, but as the bridge settled, the rest of the tubes followed suit. Brunel was impressed with the construction and had been to the site on a few occasions. He learnt from the construction and couldn't help but take some of the construction techniques to his own creations. To celebrate the bridge, 4 stone lions guard the 4 corners. The bridge, and its adjoining station, was a true success. Although the station didn't last very long, the bridge was amazing. Out of the entirety of the network, the bridge was one of the easiest and one of the least problematic bridges to maintain. Even British Rail years later did little to the bridge other than a repaint and retarring of the roof. In 1970, 2 young boys were out on a late Saturday evening when they found themselves at the bridge. They went onto the tracks and into the mouth of the tunnels. The boys found an old discarded page from a book and lit it and held it up to see better. But the boys held it too close to an old timber joint that sat between the pillar and the tunnel. The tarred old timber joint quickly caught fire, and the wind caused the fire to spread upwards and into the roof. The top of the roof, which had been coated with layers and layers of tar and hessian throughout the decades, acted as the perfect fuel. Within seconds, the top of the roof was ablaze, moving through the roof space to all 4 tubes easily and attacking the bridge from within. The air movements within the tubes fanned the flames perfectly, so that when the fire brigade arrived, almost all of the bridge was ablaze, and there was little they could do to stop it. By the next morning, the fire had burnt itself out, but in its wake it was clear that the bridge was destroyed. The tubes thankfully remained on the bridge, but the heat had caused the metal to sag and crack. The structure was no means safe, so the Royal Engineers were brought in to shore up the bridge, while the stranded trains and coaches were loaded by crane onto waiting ferries. It took 3 months just to render the bridge safe from collapse. The tubes were examined, and after over a century of hard work and service, they were considered unsalvageable. But as the tubes were dismantled, a new opportunity arose. Maybe a better bridge could be constructed. The concrete pillars were still in good shape and had held well from the fire. The Cleveland Bridge and Engineering Company took on the task of rebuilding. They wanted the bridge to be even better, but still wanted to give it its Stevenson's heritage. They too decided on a tubular design, however with a twist. Firstly, the rail deck would be more open plan. Instead of an enclosed tube, it would have no side panelling. And secondly, the roof would now hold additional weight from a road that would run above it. The twin-decked bridge would be supported by arches between the pillars. Now that access to tall ships were no longer compulsory, the arches would supply the extra support this new twin-decked bridge required, while still meeting the more modern-day shipping height requirements. The rebuilding of the bridge would last for a decade, but in July 1980, the Prince of Wales opened the bridge to the public. The upper deck would form part of the A55, one of the most stunning and beautiful stretches of roads in the UK, while the lower deck would offer rail passengers easier connection to Holyhead and Ireland. Recently, in 2017, there's been works to strengthen up the bridge and talk about raising the 4 lions to the upper deck height for cars to see. There are still memorials and markers to Stevenson's great creation. A part of the original tubing was saved from scrap and sits alongside the modern crossing, and there are plaques and reminders everywhere of what was lost. So while I look at this great ball bearing recovered from the wreck of the bridge, I hope that I've shown that everything has a story to tell. And as for the boys, the police concluded that the fire was an accident, and the boys were found not to blame. But they have on a few occasions told their own story, mainly as a warning on how one simple and seemingly innocent act can have massive and unimaginable consequences.